Dr. Tom Shih is being presented today with the 2020 Thermophysics Award for a significant contribution in the development and application of computational design tools for the thermal management of gas turbines to improve efficiency and service life. So Dr. Shih received his doctorate from the University of Michigan in 1981. From there, he worked at NASA Lewis, now Glenn, Research Center for 2 years before moving to a professorship at the University of Florida, then Carnegie Mellon, then Michigan, and then finally Purdue. At Purdue, Dr. Shih served as the head of the College of Engineering School of Aeronautics and Astronautics for 10 years. Tom became a fellow for AIAA in 2011 and has been a leader in the association, serving on multiple AIAA committees, including terrestrial energy system, standards and CFD, higher education, executive nomination, and ethics. His research areas of interest are in mathematical modeling of fluid mechanics, heat transfer, and combustion problems. So with that, I think we are ready to hear the award lecture. Thank you.
Hello, my name is Tom Shih, and I thank you so much for joining us on this talk. On the AIAA Thermophysics Award, I'm extremely honored and humbled to receive it. I want to thank my students and my colleagues who worked with me and who made the contributions possible. I also want to thank Patrick E., the chair of the AIAA Thermophysics Technical Committee and the AIA's Awards Committee for making this award possible. So again, thank you so much. What I want to do now is to give this talk, but I noticed that there's a little delay between what I say and before the slide shows up. So I'm actually just talking a little bit to make sure the slide shows up on your screen, otherwise just see me. All right, but the title of my talk is bulk temperature, adiabatic-wall temperature, and heat transfer coefficient revisited. For this talk, I'd like to thank my students, Kyle Chi, Kenny Hu, Jay Kim, Jianxin Li, Jason Liu, Ursha Pardishi, James Peck, and Zach Stratton. I also want to thank Robin Ames, my colleagues, Robin Ames, Mark Brighton, and Rich Dennis for their contributions to parts of my talk. Heat transfer plays a very important role in our lives. And this is because life is only good if the temperature is good. For me, I like weather that's around 60 to 70 degrees Fahrenheit. Interestingly, the battery, most electronics, like computers, also actually operates most efficiently around 75 degrees Fahrenheit, which is around room temperature. Although they can also, of course, operate over a fairly wide range of temperature because of environmental conditions. For gas turbines, however, they like to operate at very, very high temperatures. In fact, the higher the temperature, the more efficient. For gas turbines in fighter aircraft, they sometimes like to have temperatures as high as 2,000 degrees Fahrenheit, 2,000 degrees C, approaching the turbine blade. But the best nickel-based superalloy that we have that can resist the tremendous forces in the turbine engine and is about 1,000 C. And so in order for a gas turbine to work at those very, very high temperatures, you have to cool the turbine. And so this cooling of engineered systems to make sure they operate in the right temperatures is a discipline called thermal management. And the heat flux that sometimes we have to remove from advanced gas turbines or very advanced military avionics and electric vehicles sometimes are extremely high. And they could be as high as 100 watts per centimeter squared to even to 10,000 watts per centimeter squared. Now, 10,000 watts per centimeter squared is equal to 1,000 megawatts per meter squared. Now, for a city, an industrial city with a population of 1 million, they use about 500 to 1,000 megawatts. And, well, a city is a lot more than 1 meter squared, right? And so thermal management is extremely important, not just to make sure we can manage the temperature, but it's also very, very challenging because the heat flux can be so high. And how do you remove so much heat? Now, convective heat transfer is typically how engineers get the temperature right in high-performance computers, power generation devices, electric vehicles, and military avionics for efficient and reliable operation, as well as long service life. So I'm going to give you two examples. One's in gas turbine and one's in electronics. In gas turbines, we already mentioned that the temperature approaching a blade, especially the first stage turbine, it could be as high as 2,000 degrees centigrade. And the best material that we have that is about 1,000 degrees centigrade. It can't go above that, otherwise the material is going to melt. And so what engineers has done is they have built all kinds of internal cooling passages inside the blade to cool the blade from the inside. And this works because, let's look at this figure right here. You can see if I have a superalloy plate right here, even if the hot temperature is very hot, say 2000 C, but if I cool it, say below with 400 C, then the temperature of the superalloy will be somewhere between 400 and 2000. And I just have to cool enough to make sure that temperature is way below 1000 degrees C. Right? And so that's how internal cooling works. But it turns out we use, in addition to internal cooling, we use another concept called film cooling. And the way film cooling works is like this. If you notice on turbine blades, there's many, many holes. Well, these holes are basically, they're trying to get the cooling air that's inside the blade and somewhat to leak out or to come out of the hose, and we want these, and you see the picture schematic is shown right here. Basically, we want these cooling flows to hug the surface when they come out. So they sort of form an insulating layer, so the hot gas never touches the turbine blade, and that's a wonderful way to cool the material. And so you can sort of see a picture on this slide. On this slide, you can see that on the bottom surface here, you can sort of see part of the surface is green and yellow. That means it's the cool surface is touching that surface. That's quite cool. But the part that's not protected by the film, by the cooling flow, the film cooling flow, is still hot. It's red, right? And so this is called film cooling. Now, similarly, in electronic cooling, enormous amount of heat are generated by ICs and CPUs. And for electronics, actually, they need to operate within a fairly small range of temperature range for efficient and reliable operation. But they do generate an enormous amount of heat. And so how do you keep a stable temperature range? And so what they do is they put heat sinks by these CPUs and ICs. And these heat sinks have very, very high thermal conductivity, so heat can quickly be removed from the CPU into these heat sinks. But heat sinks also have huge heat capacity, which means you have to put in a lot of heat before you can change its temperature. So you can keep the temperature low and yet remove enormous amount of heat. And then, of course, from these heat sinks, they have all kinds of fins, either plated fins or pin fins. And then we have convective heat transfer. We have air or cooling air or liquids even, depending on how much of the heat transfer is. Sometimes we even use phase change material, like boiling, even condensation to remove the heat, to ensure that everything is cooled. Now, cooling gas turbines and cooling electronics are extremely important, and computational fluid dynamics and experimental fluid mechanics can certainly provide information to help us design the most efficient cooling system for both gas turbines, electronics, or any other device that requires thermal management. However, it turns out for complicated problems like the gas turbine, sometimes it's just not feasible. So, for example, if you want to simulate design, suppose you want to develop a cooling system for this entire gas turbine, with all the internal cooling passages, with all the ribs and pin fins that's in here, and we have done it. So you can see a picture right here in the middle of this slide. We did a simulation of all the cooling with every heat transfer enhancement feature, and just for RAND simulation, we need about 1 billion cells, and many people feel RAND is inadequate. So if you want to go to large eddy simulation, you need probably 10 billion and possibly 100 billion to get the physics right. And so basically with today's computing capabilities, it's just not feasible for us to use CFD to design a cooling strategy. But CFD, an experimental fluid mechanics, is still useful in design process. But what we need to do is we need to look at small parts of the turbine. So for example, we look at a flow through, say, a few simpler flow passages, a small part of the gas turbine, one part at a time. with pin fins, with ribs, and studying tremendous detail, and then encapsulate that understanding into a very, very simple model. And then from that model, then we can use to design the entire cooling system for the gas turbine or for other devices. And convective heat transfer from a solid surface is typically characterized by the heat transfer coefficient and defined by Newton's cooling law. And I think everyone is familiar with this law because it's the first course in heat transfer. And it turns all the physics that you get from the CFD or from the experiments are embedded into this heat transfer coefficient. And this heat transfer coefficient from the cooling also is defined based on a reference temperature. And that reference temperature is the effective temperature that drives the heat transfer to or from a surface. Now, typically for fluid mechanics, we classify two classes of flows, external flows and internal flows. External flows are, for example, flow over an airplane. But let's look at a simple case. Let's just look at flow over a flat plate. If you have a very hot gas from a flat plate, you can see you have a boundary layer over the plate. Now, for such a problem, you can clearly see that the effective temperature driving the heat transfer is the temperature that's approaching the free stream temperature. So it's very simple. So the reference temperature for external flow is simply the free stream temperature. Now, for internal flows, so for example, suppose the wall is very hot and you want to keep it cool, and so you may bring some cooler fluid in. But you can see if I bring cold fluid in, it will just get hotter and hotter because as I cool the walls, my fluid gets hot. And so you need something to measure the capacity of that fluid to absorb more and more heat. And that temperature is defined as the bulk temperature. And bulk temperature is a mass flow rate weighted, also a specific, the formula is written right here. And so it turns out both the free stream temperature for external flow and bulk temperature for internal flows are well established and well known in any first course in heat transfer. So what's the problem? Well, let's look at external flow. Now, the boundary layer flow is very simple. But in reality, or practical problems, the problem is never that simple. So for example, with gas turbines, we already mentioned that you have film cooling. So when you have the flow over the blade has hundreds of holes. All those holes are ejecting fluids of different temperature. So if you look at the picture here, you can see for this surface right here, you can see when you have film cooling, it's cooled on that surface, but part of it still see the hot surface, right? So when you have a surface that sees the cooling flow from all the different holes, it's different sources of temperature coming through, and you have this hot gas on top. So which temperature do you use? So it gets a little bit confusing, right? So the problem is it doesn't look as simple as it is now. Now for the bulk temperature, even though the concept seems so precise, but now suppose I have flow around a bend. And suppose I have flow separation. Now, which cross-section do I take? Which one is meaningful? If I take a flow, for example, around this one, this picture in the middle is for an L-shaped duct, is for the trailing edge of a gas turbine. You have all kinds of ribs. You have now, which cross-section do I take to define the bulk temperature? So if you don't have the right cross-section, what does it mean? And so you can see there are quite a bit of complexity and issues. So in this talk, what I want to do is address issues and challenges, how to define the reference temperature for external flows and for internal flows, and also what are their effects on the heat transfer coefficient. So if you chose the wrong reference temperature, so what would it do? And the other question is, and if you suppose you did do it correctly, now how useful is the heat transfer coefficient in design of a very complex heat exchanger or cooling system? So I'm going to talk about internal flow first, not external flow. Let's start with the internal flow. Now, we already said for internal flows, the reference temperature in the Newton law of cooling to define the heat transfer coefficient is the bulk temperature. And the formula was already given, but it is this integral right here. And it's a mass flow rate weighted temperature, and that also account for the specific heat of that particular fluid. Now, it turns out that's one formula, but it turns out you can also get the bulk temperature another way by applying the energy equation to some control volume. So for example, if I want to find out the temperature at a, say, cross-sectional area I, right? If I draw a control volume to that, include that particular control surface up to, say, to the inlet, if I know everything that all the energy that comes in from the inlet, and I know all the heat that goes through all its control surfaces and apply my energy law, I can figure out the bulk temperature at this control surface. And it turns out you can do either way, you get the same temperature. All right, so what's the big deal? Well, the big deal is, in order to get this bulk temperature by whichever method, I need to know the velocity profile. Every cross-section, I need the temperature profile every section. So you can imagine if I'm an experimentalist, and I need the bulk temperature, not just in one cross-section, I need hundreds and hundreds of cross-sections, right? So for each cross-section, and if it's 3D, I had to measure the temperature, the velocity, every point. I mean, this gets to be enormously tedious. And sometimes we may not have optical access, not so easy to measure. Experimental methods are not so easy either. And but computationally, it turns out it's a very, very easy problem because computation, we have solutions everywhere, but nobody believes CFD. I work in CFD and I know people only believe experiments, but experiments are not so easy to do. But in CFD, we have our challenges too. But whatever, but that's one challenge. But what are other challenges that affects both the computations and experiments? Well, which cross-section? We mentioned that a little bit earlier. So if I have a flow around this U duct, what cross-section do you use? Well, I have worked with industry on this problem, and I found there's many different definitions. There's quite arbitrary. And I found that it really doesn't matter. But you have to know which cross-section they used and how they define the bulk temperature. If you don't know how they define the bulk temperature, then you will not know how they actually got the heat transfer coefficient, and then how can you use that heat transfer coefficient to design. And the reason I'm highlighting this point is because most papers that you read, they do not tell you how they calculate the bulk temperature. They just give you the final formula. And so if you are going to use that formula, I'm challenging you now that you better understand how they calculate the bulk temperature and how they define the cross-section. Now, as I said, because the bulk temperature is very hard to get, you find that many experimentalists and many CFD folks, when they don't use the bulk temperature, they use an approximate bulk temperature. And so some of the approximate bulk temperature people use is some people just use the temperature at the inlet because I know the inlet perfectly, all right? And some people use the surface temperature because they know the wall temperature. And sometimes they use the average temperature between inlet and the wall temperature because they can count the two. And there are others, of course, that measure the temperature at the inlet, they measure the exit, and they do linear interpolation. Right? So all of these approximations. So what are the consequences? Well, let's look at this curve here. But before I go there, I just want to mention one thing. So suppose I get this heat transfer coefficient by using CFD or experimental methods. And so I could calculate this H everywhere. And so, but once you get the H, we always non-dimensionalize because we're talking about dimensional analysis, we're talking about similitude and design experiments. So non-dimensional heat transfer coefficient is a Nusselt number. So let's look at flow problem. Suppose I was looking at flow past a circular cylinder, and suppose the temperature of the air coming in is 1,270 degrees K. So at this time I have hot gas coming in. I have a wall that's cold at 573 degrees K. And the Reynolds number is 15,000. This source gives you the flow rate. Now, this problem is clearly compressible, even though the velocity isn't low, but because the temperature is so great, the density varies like crazy. But if you assumed that the density doesn't change and all of the transport property are constant, then the Nusselt number will look something like this. This is the Nusselt number on the y-axis. Along here is the distance along the tube. You can see it's, the Nusselt number is very high, then it drops very quickly, then it becomes constant. And this is what you can see in the textbook. But of course, the flow is really compressible, and the properties are really temperature dependent. So if you really did the problem correctly, you'll find that the correct, if you use the correct bulk temperature, you'll find the Nusselt number is actually this line right here, is this blue dashed line. So this is the correct answer. But if you used the inlet temperature as the bulk temperature, and that's a convenient one to use, but that bulk temperature will never change. Whereas in this real problem, the bulk temperature, it comes in as hot, but the wall is cold, so it's going to get cooler and cooler as it goes along. So the correct answer is this one, but if you use the T inlet, you'll get this line. So you can see this considerable error between the Nusselt number that you get if you use the inlet temperature, and this Nusselt number you get if you use the correct bulk temperature. And in fact, by the time you reach hour D about 70, the error gets to be about 30%, which is quite appreciable. And I don't think you want to design anything with the error that's already 30%, which is huge. All right, so now the point I want to emphasize here is that when you have complicated problem, the cross-section that people use to define bulk temperature could be quite arbitrary, but you have to know what they are. But the bulk temperature must be the correct bulk temperature. It cannot be the T inlet. It must be some approximation of getting pretty close. If you do linear interpolate, maybe it's not so bad, just linear interpolate pretty close within points. But for example, when you have flow over an array of pin fins, this is what people do for bulk temperature. Because it gets really complicated, so they measure bulk temperature across section between pin fins, between rows of pin fins. So here's the pin fin row, here's the pin fin row. So they measure the temperature, the bulk temperature at this row, between the pin fins, and they measure the bulk temperature here at two cross sections. Then they average these two bulk temperatures. All right, they don't even linear interpolate; they just average the bulk temperature. Then they use the average to calculate as the bulk temperature for this entire region that's sandwiched between those two control surfaces. Then they use that bulk temperature to calculate heat transfer coefficient for everything in there. And so, but if you understand it, then you'll know how to use that information. All right, so let's now understand. So from CFD or for experiments, if I study a problem, I can provide you a heat transfer coefficient. Let's see how good it is. What does it do? Well, it turns out Perkins, Warsaw, and Schmidt in 1965, they did a very careful experimental study, and a very thorough one. They studied the flow in a straight tube or duct of circular cross-section, and it points normally upwards, so it's aligned with the direction of gravitational pull. It's a very long duct. Its LOD is equal to 160. All right, so it's plenty long to pass the entrance region and also plenty long to reach nearly fully developed flow. When I say fully developed flow, I'm just saying, of course, for compressible flow, there's no such thing as a fully developed flow, but it is not affected by the entrance region. And they studied a wide range of T surface to bulk temperature from 1 to 7, so it's huge. They also studied a very wide range of Reynolds number, which is flow rate through the tube, from 18,000 to almost 280,000, so very wide range. But these are also the Reynolds numbers that's encountered in industrial gas turbines. And now for each of these configurations or temperatures and operating conditions, they measure the velocity of many cross-sections. They measure the velocity, they measure the pressure, they measure the surface temperature, they measure the bulk temperature, they measure the heat flux. And then once they have that data, then from that data, they computed the heat transfer coefficient at each cross-section, the Nusselt number of that cross-section, the Reynolds number of that cross-section, the Prandtl number of that cross-section, and the temperature ratio of that cross-section. So what did they do? So they got all this data, and they just did some data mining or data analysis. And when they get done, and today we'll call it data analytics, but when they get it done, what they found is this. They found that well, dimensional analysis is wonderful, it works. And it's this plot right here. They found that the Nusselt number, which is defined as the heat transfer coefficient, and it's all local data. It's every cross-section, all the experiments we have done. Dump it all together and figure out. And they found it's the heat transfer coefficient, the hydraulic diameter of the pipe, in this case just diameter of the pipe, and K, the thermal conductivity of the fluid, and it must be evaluated at the bulk temperature, is a function of the Reynolds number, the Prandtl number, and the temperature ratio, and of course, maybe the location, if it's maybe in the entrance region or something. And it turns out the formula they get is that when they look at all the data, my God, it collapses onto one straight line. I mean, there's some deviation, and it's a long plot, so there is some degradation, but pretty much so, it collapses on one curve, and there's the equation for that particular curve. So by the way, this is the reduced order model that one gets when we do CFD, or if one does experiments. And so instead of having this massive amounts of data, for each configuration, such as straight tube, we can provide a formula as general as this. And of course, for this particular data is valued within this Reynolds number range study and this temperature range study. So how to design with this Nusselt number reduced order model? Well, now, for many different configurations, if I did many study on many different configurations, you'll find basically that if you have this formula, once you obtain such a reduced order model for Nusselt number obtained for one configuration, one can then get the heat transfer coefficient and the heat flux in any other geometrically similar configuration if you know the Reynolds number, the Prandtl number, temperature ratio. And so basically, if I'm going to design something, and if I'm analyzing it, and if I have one location, I say, oh, I know the Reynolds number there, I know the Prandtl, And I know how much energy I will have by the time I reach that cross section. This is surface temperature. So what would be my heat transfer coefficient? Well, you just use your Nusselt number formula, and you can figure out what the H is. And then, of course, once you know H, then you can calculate the heat flux by using Newton's cooling law. And once you know what that is, then now you know how much energy to take away from the bulk temperature, and you progress upwards. And so you can keep analyzing, for example, how much energy that's still contained in the fluid that can continue to keep cooling the heat exchanger, or keep heating it, one or the other. And so this formula is really quite interesting, because a formula like the Nusselt number, a model like Nusselt function, Reynolds, Pareto, and temperature ratio, it actually behaves like an equation of state. See, when you do an equation of state like P equals rho RT, if I know the pressure and the temperature, it doesn't matter what configuration or what geometry. If the condition is such that the thermally perfect gas model is applicable, if I just know what the temperature is, if I know what the pressure is, I immediately know what the density by the equation of state. Well, here what we're trying to say is, if I have a geometrically similar configuration, if I know the Reynolds number, if I know the Pareto number, if I know the temperature ratio at that point, or that cross section, I immediately know the Nusselt number there. And if I know the Nusselt number there, I can immediately figure out what the heat transfer coefficient there is, and also I can immediately figure out what the heat transfer, the heat flux is. So this is an incredibly powerful formula. And so this is the ultimate goal. So when we do CFD or we do experiment, and that's the kind of formula we want to present. But the reason, even though many of this is well known, but the point I want to emphasize here is that, well, you must get the bulk temperature, right? And you must know what cross-section they define the bulk temperature, because the geometry is very complicated, and it's not just a straight pipe, right? And so how do they do that? And it must pay attention to it. And everything we're saying, how wonderful this scaling and dimensional analysis works, for example, how general this model is, like an equation of state, it only works if you use the correct bulk temperature, otherwise it doesn't. All right, so let's now talk external flows. Now, for external flows, we already mentioned earlier, the challenge is that the reference, if there's only one temperature that's approaching a flat plate, and then we know just the free stream temperature is very easy. But if I have a problem, I have 10 different holes, and I have a hot gas going over the surface, but I have many, many holes on the surface that's also ejecting different fluids at different temperatures, and it gets very, very confusing. So what temperature do I use? Well, the current approach is to use a temperature that we call the Adiabatic-Wall temperature. And so I'm going to denote that as TAD. Typically in literature they call a wall AW, but anyway. So what does that mean? Well, it turns out the adiabatic-wall temperature is a generalization of the free stream temperature. Because if there's only one temperature, you'll find that the adiabatic-wall temperature collapses to the free stream temperature. I have a typo here. This B should be AD. Now, the current practice assumes that the adiabatic-wall temperature depends only on the flow, only on the property of the fluid, and only on the geometry of that surface. And is completely independent of the surface temperature, is totally independent of any heat transfer that's taking place on the surface. So the way that people are trying to get the T adiabatic-wall temperature is that they always assume that the T adiabatic temperature is the temperature that you get if you keep the wall completely adiabatic. So for example, if I have this film cooling flow coming, and if this wall and this is, so I have hot gas going over this film cooling hole, and this is the jet that's coming out, and so on this surface, so if this wall is completely adiabatic, then you can sort of see anywhere it doesn't have film cooling jet, it's just going to be equal to T free stream. But anything with a film cooling hole, then you may have some different temperature. And of course, this hot gas and this cooling flow may mix. But whatever temperature that I get on the surface, if the wall is adiabatic, that is my adiabatic wall temperature. So that's the definition. Right? So in this part of the talk, what I want to do is to examine, are these assumptions correct? And does it make any sense? And I like to also examine the existing methods used to compute the adiabatic wall temperature. And I'm going to examine this by using a very simple test problem. Now, for the rest of this talk, I'm taking the material from a paper that it's this year's IGTI paper. It's a paper by two of my students, James Peck and Jason Liu, and also my colleague, Mark Bryden at Iowa State and DOE Ames Lab. And so send me an email, and I'd be happy to to send you this paper. All right, so this is a test problem. So I'm going to study a film cooling flow over film cooling of a flat plate. So basically, we have one row of film cooling holes, and the film cooling hole is basically an angle hole right here about 35 degrees. So I have jet cooling flow about 400 degrees C, and it flows over this flat plate, and the goal is to cool this flat plate. And the hot gas is 1,500 degrees Kelvin, so that's the hot gas, all right? And I won't go into details of the geometry, but I think this is the problem. And we're going to, now for this particular problem, we're going to study one case in which the wall is completely adiabatic. Because if it's completely adiabatic, that's the adiabatic wall temperature. We're also going to study this problem with many different temperatures, because depending on what my cooling temperature is, you can sort of see, because my cooling temperature is 400, and my wall temperature, my hot gas is 1500, but my wall temperature could be anywhere from 400 to 1500. So I'm going to study a wide range of surface temperatures, all the way as low as 400, actually below 400, and to even higher than 1500. So I'm going to look at an entire range of temperatures to see how does different methods for evaluating the adiabatic temperature work and this effect on heat transfer coefficient. Okay, so that's the problem. All right, now for this film cooling problem, this is a pretty standard film cooling problem that many experimentalists have studied, or pretty similar. But in this study, in the CFD, I'm just going to use a steady RAS study. At least my students actually did all this work. So with the steady RAS is a compressible, soluble average continuity momentum energy. And the gas is assumed to be thermally perfect, but the properties, thermal conductivity, viscosity, are all temperature dependent. And of course, specific heats are temperature dependent as well. And the turbulence is modeled by the realizable K-epsilon model. And we do not use wall functions integrations all the way to the wall. Now, the code that we use to do the simulations is the ANSYS-Flint version 19.2, and we use double precision. The algorithm to obtain solution is simple: second order accurate upwind for all advection terms, second order central for all diffusion terms. Since we're interested in steady state, and it's simple is a segregated algorithm, so we obviously iterate, and we keep iterating until the solution plateaus. And once it plateaus, the larger residual is less than 10 to the minus 6. All right, so and for CFD, one of the first things we have to do is want to make sure the solution we generate are grid independent. So we did do a very careful grid independent study, so I'm not going to go into details. A few points I want to make is that we did use a structured grid. The grid quality is quite good. It means it's quite smooth and nearly orthogonal everywhere, except a few locations, because you have to remember the hole is coming at an angle of 35 degrees. The first point away from all solid surfaces has y plus less than 1. And we actually use a constant grid spacing of 3, a constant grid for three cells. And the reason we want to make sure we maintain second order accuracy next to surfaces, because for us heat transfer is something we want to make sure we capture very, very accurately. And so we did a wide range of study. The number of cells we examined went from as low as 0.94 million. We actually only looked at one hole, basically, up to 15.6 million cells. And so we did a very careful grid sensitivity study. We're having a thunderstorm tonight, and that's what you're hearing. And in this grid sensitivity study, I won't go into detail, but I want to show you that we did do a very careful study. And one thing that's very, very important for us to resolve is where the heat flux, when you have film cooling, and we want to know exactly where the heat, if you have an isothermal wall, for example, where does the heat transfer, where the heat transfer is positive and negative. So, and these are the blue and the yellow lines. And it turns out we make sure that we can capture that accurately. All right. So if you have some confidence in what we have done in CFD, then we try to be as careful as possible. So let's talk about how we measure or compute the adiabatic-wall temperature. By the way, we're doing CFD, but what we're trying to do here is whether we do experimental or computational, it's the same thing, but except we're simulating. If you're doing the measurements, we're simulating that measurement. All right, so method one, there's two methods that's widely used for getting the adiabatic-wall temperature. The first one is you run a case with adiabatic wall. This, of course, is very, very easy to do with CFD. But for experiments, it's quite hard. So the method one is trying to actually mimic a adiabatic wall surface. But so if you do an experiment, you try to choose material with very low thermal conductivity and very low heat capacity. And maybe you can use guard heater to make sure that you truly have no heat transfer across the surface. But usually people don't use guard heater, but you could. But then you have sensors and things like that. Okay, but basically you run one case. Now, whatever temperature, when you get done, whatever temperature you get on the surface of that flat plate that you're trying to cool on turbine cooling, that's the temperature we call adiabatic-wall temperature. We assign that temperature that you get on the surface with adiabatic-wall is adiabatic-wall. If you do CFD, it truly is adiabatic-wall. If you do experiments, it's a little bit hard because you always have some conduction. Now you run a case that's not adiabatic, which means you could run isothermal, but it doesn't have to be isothermal, but you run some cases that have heat transfer. Now for that problem, you have to measure the temperature on the surface and the heat flux at every point on the surface. And if you know the temperature, you know the heat flux, and from this equation, the Newton law of cooling, and since I have the adiabatic wall temperature for the case that I did earlier when I did adiabatic wall, remember that's the adiabatic wall surface temperature you get for every point on the surface, now I can get a heat transfer coefficient at every point on the surface. Okay, so if you use this approach, you can sort of see that the TAD is completely independent of surface temperature and the heat flux anywhere on the surface because I obtained it, or we obtained it, by assuming that the entire surface was adiabatic. Now, the second method is as follows, because the adiabatic wall is very, very hard to mimic experimentally. And so what they try to do is the following. They say, oh, how about this? Let's measure two isothermal cases. So they measure the heat flux for two different temperatures. So they'll have maybe one, they will have that, they will do, for example, the problem we just talked about, they may do thermal, they may do one isothermal wall maybe at 1,000 degrees. They could do another one at, say, 1,100 degrees. They do two, right? Two temperatures. And then for each of those two temperatures, they will get the heat flux every point on the surface. But for every point on the surface then, for every point on the surface, they have to make two measurements, right? So for a given point on the surface, so now they make an assumption. They're saying that the heat transfer coefficient, any point on the surface, depends only on the ratio of the heat flux and the temperature difference, Ts minus T adiabatic wall. And they assume the T adiabatic wall is independent of the, again, surface temperature and the heat flux. So if you look at Newton law of cooling, you can see the heat transfer coefficient is Q divided by Ts minus T adiabatic. So if I have one temperature measurement, one heat flux, one temperature, because every temperature different, you get a different heat flux. And if I do the same point, but a different temperature, and I get different heat flux, well, the H for both must be exactly the same. That's the assumption they're making. And if they're the same, then if I just equate two equations, because I know QS1, I know TS1, I know QS2, I know TS2, I can calculate TAD. And of course, once I figure out TAD, then of course I substitute TAD here, now I can get HAD. So that's the method two. Right? Let's see how good the methods are. Let's evaluate method one first. So method one is you get the adiabatic wall temperature by imposing adiabatic wall. And I'm going to denote that adiabatic wall temperature was a C. So it turns out if you use this particular technique, it is interesting in that it is unique because regardless how complicated the problem is, I'm just saying I'm going to impose adiabatic wall. And so once I finish, I get one temperature on the surface, and that temperature is adiabatic wall temperature. Now, but this is the problem. If you use that approach, you'll find that I'm going to show you three problems right here. So here I have the adiabatic wall temperature, all right, but I'm going to look at three different surface temperatures. I'm going to have one surface temperature 800 degrees, another surface temperature 950 degrees, another surface temperature 1,100 degrees. Now it turns out the white lines that you see right here, the white lines, these white lines are the temperature in which the surface temperature 800 minus the adiabatic wall temperature that you got from the adiabatic wall simulation or measurement is equal to 0. So the white line is here. So if it's 800, that white line is here. If the isothermal wall temperature is 950, that white line is here. Right? And if it's 1,100, the white line is here. Okay, so, but that's the problem. The problem is at these lines, where the heat flux is non-zero. So when the surface temperature is equal to the adiabatic wall temperature you get from the adiabatic wall, at those lines, the heat flux is not zero. But the heat transfer coefficient is the heat flux divided by Ts minus T adiabatic. And if this number is not zero, this thing goes to infinity. So the heat transfer coefficient is infinite along the lines that's white. Right? They don't match. And so that's the problem. The actual line where the correct adiabatic wall temperature is actually somewhere else. You see the blue and the red. Let's look at this particular case. When the wall temperature is 1,100 degrees C, the coolant temperature is coming here. So the blue is colder than the wall. So the wall is positive, the heat flux is positive. The wall is transferring heat to the surface. The red is the wall is 1,500. The wall, the hot gas is 1,500. The wall is 1,100. So the heat transfer is negative because heat is going into the wall. The line that separates the blue and the red, that line is where Q is truly zero, because when it's positive and negative, you have a line that is zero. So that's really where the adiabatic wall, that line should be. But the adiabatic wall temperature is not predicting that. Okay. So basically what it's saying is that the assumption that the adiabatic basically shows you that it's wrong. But even though I say it's wrong, later I'm going to show you this a little bit more detail, is that actually the T adiabatic wall that you get by the adiabatic wall temperature is still surprisingly good, right? Because you can sort of see that if it's 800, it's actually compares pretty close to the right one. And 1100 gets a little bit worse, all right? But it's still pretty good because the temperature is changing enormously here. So, and it turns out later you find the T adiabatic wall temperature is only off by about 10%. So, and that's why I think people have not been paying attention, because the adiabatic wall temperature is actually pretty good. And if you're using adiabatic wall temperature to get adiabatic effectiveness to see how good film cooling is, it's still a pretty good indicator of how good this method is. But the problem is in getting the heat transfer coefficient. But if heat transfer is important too, then, even though, H is infinity at when Ts is equal to T adiabatic is not, for example, along lines of white, it goes to infinity. But mathematically, you can sort of see if Q is not zero, but this is zero, it's infinite. But if Q is not zero, but Ts minus T ad, if it's not zero, but it's still a very, very small number, I mean, you still have a huge H, right? And so this is the heat transfer coefficient you will get for this problem. And if you use adiabatic wall temperature by assuming adiabatic wall, this is what you get. You get a huge heat transfer coefficient. Actually, we only plotted up to 2,500 for the heat transfer coefficient also in terms of watts per meter squared K. But actually, it goes to infinity. And the correct pattern is this one right here. Later, we're going to show you how to get the correct one. So this is the correct heat transfer coefficient at this temperature, 950 C. So this is the correct profile. This is what you get from the adiabatic wall temperature that you will get by assuming adiabatic wall. So you can see it's way, 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 way off. All right, let's look at method 2. Now, method 2 looks very rigorous, but let's look at an example. Suppose, again, I have T cool of 400 degrees and T hot 1,500 degrees. Now, I need to, at every point, so let's look at this point. Every point, I need to have two pairs of temperatures. So the question is, which two pair? So what we have done here is, I'm trying to find, so I'm going to choose temperatures, T1, T2. I'm going to use 5 different temperatures. So you see 5 different temperatures there. So I actually chose 5 pairs of temperatures. And for every temperature at that point, I'm looking at that one point, but I'm looking at 5 isothermal walls. And for every thermal wall, I figure out the heat flux there. So I have 5 pairs of QS, TS, right? So now I can connect, now the question, which 2 points do I use to calculate my T adiabatic wall? I can combine 1, 2, 1, 3, 1, 4, 1, 5. So these are the straight line. Wherever it crosses this line Q equals 0 is the adiabatic wall temperature. So you can see there's a lot of possibilities. Or I can do 1, 2, 2, 3, 3, 4, 4, 5, another various combinations. And so I get, again, all kinds of solutions. By the way, the green point that you see here is the adiabatic wall temperature that you get by assuming adiabatic wall. And the other intersection is what you get if you use this particular method. And so even though, so each pair, so then basically if TAD, and I'm denoting the adiabatic wall temperature that you get by this method is TADE, all right? So you can see so each pair gives you a different adiabatic wall temperature. Clearly, the heat transfer coefficient is also not unique. So this is a hard problem. So I'm just trying to show you the errors. If you look through the errors by computing, this is actually the different adiabatic wall temperature they will predict by choosing different points, right? And again, this is the point that you get by adiabatic wall temperature if you did adiabatic wall. Now going through, in this particular study, I looked at 5 different temperatures, and if I go through that entire line, if I go back up, if I go through this entire line, all right, you see that previously I only showed you 1 point. But if you go through a line of different points along that line of y over d, x over d equals 1, that particular location, you find that, okay, remember the coolant temperature is 400. The hot temperature is 1500, which means the temperature, adiabatic wall temperature, cannot be below 400. So you can see some of the predictions along the line are indeed above 400. But you also get a bunch that's below 400. And but you also get temperature even below 0 degree Kelvin, and so which is ridiculously wrong. So I think what I'm trying to show you that is this method also has challenges. But it turns out this method, you could get very accurate answers if you happen to choose 2 points that's very, very close to the correct adiabatic wall temperature, then you could get the right answer. But because the coolant temperature and the hot gas temperature usually is quite different, and so then you have to look through the entire range. So it's hard to know how to guess which 2 is the right one. So basically, you need a better method. And so this is our paper. This is the paper that my student, James Peck, Jason Liu, and my colleague, Mark Brighton, we were presenting at this year's IGTI meeting. This is the observation we made. So previously I showed you 5 points. Now suppose at that particular point that you think is diagram, suppose I start going from 5 points to 15 points. We added more and more points. What we have found is, interesting. They all converge to a single value. What we have found is that the adiabatic wall temperature does depend on heat transfer, but it truly is independent of surface temperature. And so we develop a method. To figure out this, because we found that every point, if you have a lot, they all pass through 1 point. And that point we found is independent of surface temperature. So we develop a method, right? And I'm not going to go through this entire method, but basically, the more points, the better. So I'm going to go maybe kind of quickly. Let me go over it. It involves 6 steps, all right? So basically, if I want to get the adiabatic wall temperature, I need to get n isothermal walls, all right, or different to n surfaces. The bigger the n, the better. But I'm not going to show you here, but in this paper we found that n equals 5 is not. You need at least 5 isothermal walls. And these 5 isothermal walls, one thing that's very, very important is that they must span from the coolant temperature, a little bit less than the coolant temperature, to a little bit higher than the hot temperature. So if your coolant temperature is 400 degrees, your hot gas temperature is 1500, you have to go from a little bit below 400 to a little bit above 1500. And you have to subdivide those into 5. And there's a way to do this, and my student, it's in the paper we show you, not here, but the paper explains it. Okay, so now for each of those 5 isothermal walls, you have to do a simulation or you have to do a measurement. And for every one of those surfaces, you know the temperature, because that's the temperature imposed, but now you have to calculate the heat flux every one of those surfaces, right? And so that means you will know the heat flux, the function position on the surface, x and y. Okay. Now you have to interpolate. Basically, you have to construct an interpolation, a function, sort of like this, right? This is the interpolation for a point. So I have all these, but I only have 5. I only need 5, but here I have 15. So you have temperatures for that point for different heat. So here's temperature, here's heat flux, and here's temperature. And so I will have 5, and I have to fit a curve between them, right? But this is for one point. But I have to do that for the entire surface, for the entire 5 surfaces, right? So it's a transfinite interpolation. Now, once you get that thing interpolated, now you have to do a root finding routine. So now you have to find the root. So for each point, you have to find where that value is. So you first interpolate this function, but for the entire surface, that's the transfinite interpolation. Now you have to find the root routine. You have to find the roots for every point. And so once you find that root is the adiabatic wall temperature at every point on the surface. But you have to find every one of them. And that's okay. Then once you have the adiabatic wall temperature, now you can calculate the heat transfer coefficient. And the details are here. And it turns out if you use the method that we have developed and presented right here, you'll find out that for this method, whenever the adiabatic wall temperature equals Ts, the heat flux is truly 0 there. And that's the important point. And so if you use our method, you'll find that this is what the adiabatic wall temperature should look like. And this is what the heat transfer coefficient should look like. Now, we didn't, and now I'm going to compare it with an existing method. I'm not going to use the QS-TS2 measurement combination because there's infinite number of them. But if I use the adiabatic wall temperature one, because that's unique, and if I use that one, you'll find that the error in the adiabatic wall temperature by using the adiabatic wall boundary condition approach. And this is the error. The error, you can see, is about 10%. It's actually, most of it could even be less than 5% or 6%. So the error in the adiabatic wall temperature is not so large, at least not for the example that I have illustrated here. But the heat transfer coefficient is huge. Even though I only put the error up to 100, as you know, on long lines where the heat transfer, the heat flux is not 0, but the surface temperature equals adiabatic wall temperature, the heat transfer is infinite. So the error there is huge. And so bottom line here is we did develop a method that guarantees that when the surface temperature equals the adiabatic wall temperature, the heat flux there is truly 0. And with our method, we can assess the errors in existing methods. All right, so now does the heat transfer coefficient depend on Ts and Qs? And it turns out we looked at five different temperatures and we found it indeed does. So we find that even though the adiabatic wall temperature is independent of surface temperature, but the heat transfer coefficient is a strong function of temperature. It could vary up to 40%. And this is important to note also because often in their lab, because right now most of us trust experiments. Nobody trusts CFD. Maybe they trust us a little bit if we do LES. And even then they'll argue about how well do you do grid sensitivity. And we try everything we can, but it's very easy to argue against these computations. But people believe experiments. But what I want to show here is that in an experiment, for example, TS1 is near the room temperature. It's what typically experimentalists do. But the reality is a very different value. It could be off by 40%. And so we do need experiments to maybe validate the CFD or to show how far off our computational models are. But once our CFD is modeled, we could actually provide you the information. We could tell you how the heat transfer coefficient is a function of temperature, so that we could provide you that Nusselt number model. Nusselt number is a function of Reynolds, Pareto, and the temperature ratio. So let me come to the summary. Heat transfer plays an important role in our lives in getting the temperature right. And it's a domain that's called thermal management. Though CFD and experimental methods have come a long way, design of cooling systems still require the use of reduced order models that use the heat transfer coefficient. But the heat transfer coefficient, but that heat transfer could be provided by CFD or by experimental methods. The CFD and experiment are still quite useful. The heat transfer coefficient in Newton's law of cooling is amazing in that the Nusselt number is a function of Reynolds, Pareto, and the temperature ratio scales for geometrically similar configurations and can be used like an equation state. However, the reference temperature must be right. Now, for internal flows, the heat transfer coefficient must be obtained by using the bulk temperature. And for external flows, you need to use the adiabatic wall temperature. Though errors in the adiabatic temperature obtained by enforcing adiabatic wall condition is less than 10%, the error that it creates in heat transfer coefficient is huge. Getting it by measuring the temperature and the heat flux at 2 temperatures or 2 different heat fluxes also can create substantial errors in the heat transfer coefficient. And the reason is that both methods do not account for heat transfer on the surface. And we already mentioned in this talk earlier is that the adiabatic wall temperature truly does not depend on the surface temperature, but it does depend on the heat flux. So a new method has been developed that does yield the correct adiabatic wall temperature and the correct heat transfer coefficient. And please see this paper for more details. And this method can also be applied to both computations or to experiments. All right, thank you so much for your attention. And I'm not sure we can have questions or not, but if we not, maybe send me an email. I'd be more than happy to talk to you. All right, again, thank you so much for attending this talk. Thank you.
Well, thank you, Professor Shih, for the very interesting talk. So with that, I think we're ready to take some questions. So I believe there's a Q&A feature that you can use to do that.
Okay, thank you, Alex, and I apologize. I didn't realize our the new chair for the Thermophysics TC is Diane Pytel, and so I'd also like to thank her as well. I don't see any questions from the list, so, but if there are any questions, I'd be happy to answer.
Attendees, there is a Q&A button at the bottom of your screens. If you'd like to type in a question, please use the Q&A function. Thank you.
Yeah, well, maybe if there's still people attending, I guess there's still few people attending. I guess the key point of this talk is that lots of there's heat transfer. Well, thermal management is important. Hard problem. You have to get the bulk temperature right, but in this particular paper, we basically developed a new method to get the adiabatic wall temperature right. There is another method which I did not talk about in this paper. Bob Moffett started an idea that uses conjugate heat transfer. He used the Green's function, so he did try to account for heat transfer. He was working on electronic cooling, and we're still evaluating his method. And John Eaton have used inverse Green's function to study this problem. And so the way he works is he is trying to use Green's function to figure out how much heat when the coolant flow is going through, he's trying to figure out what heat transfer has taken place. But that method, we're still also not sure if it will satisfy the condition that when T wall equals T adiabatic wall, will the heat flux be zero there? So that's the criteria that we're trying to satisfy. So, but we're checking on that method right now. But that's the only method we know that actually tries to account for some of the effects of surface heat transfer. Can you hear me? Okay, all right, thank you, Angie. All right.
So there is one question. So somebody is asking to provide again the reference of the paper.
Okay, the reference on the paper is an IGTI paper. How about this? Let me give you my, because I don't have my access to my computer right now since I'm using it. But my email address is tomshih@purdue.edu. It's TOMSHIH@purdue.edu. If it's hard to get to, just Google me. Just say Tom Shih I have to say Purdue University. There's still a bunch of Tom Shihs in this world. So you send me an email. I'd be happy to send you the paper. And can be used. Did someone say something?
So is there more questions? If you have a question, please type them up.
Yeah, maybe one more thing while we're waiting for questions is that when I said the Nusselt number behaves like an equation of state, I guess for equation of state, if I know say P equal to RT, if I know P and T anywhere, I will know rho at that point. And so it's interesting that if I know Prandtl number, Reynolds number, temperature ratio at a certain cross section, I will know the Nusselt number at that cross section for if the problem is geometrically similar. But with that said, I just want to mention that P equal to RT is pretty accurate. But with the Nusselt number, what we have found, the error is about 10%. But if you read most textbooks, they often tell the Reynolds, the Nusselt number could vary by as much as 40, something even more. And the reason the error is so great is because they actually use incorrect bulk temperature. But for the adiabatic-wall temperature for external flows, it's actually a much more complicated problem because we have so many different free stream temperatures. And so the concept that we mentioned here actually is applicable to external flows as well. That have many sources of free stream temperatures, and so even though here we didn't consider viscous dissipation is accounted for, but of course for much higher Mach number flows, viscous dissipation, other physics come into play as well. But this method should work as well. Just let you know some of the new ideas we're currently working on is that so far we only tried everything for constant temperature. We're now looking at cases when the temperature on the surface is not constant. So for example, maybe because maybe sinusoidal temperature, because for example, when the film cooling first comes out, the temperature on the surface does change, it's not uniform. And so we're trying to understand some of those effects. We're trying to understand the effects of conjugate heat transfer. So we're also continuing to study this problem. And this is actually our next paper. Most of our work is done. So we're trying to develop a generalized formula for Nusselt number for film cooling flows, for classes of film cooling flows. That's what we're trying to do.
So I might have a quick question if I am allowed to say it live. So I've never dug into this myself, but somebody mentioned to me at some point, one of my colleagues, that there was somebody called Adiabatic that wrote a book called New Engineering, and he was revisiting this idea of the Newton's law of cooling and completely rederiving it, somewhat similar to, well, the idea that you presented. I was wondering if you were familiar with that.
I am not. Maybe if you have that reference, send it to me. I'll be happy to read it. But I have to say,
I'm sure it's applicable, though. That's a conversation I had a long time ago, so I was just wondering.
I have to say, Newton is an incredible guy. I mean, he F equals ma, universal law, universal gravitation. But that equation looks so simple, and a lot of it, but it works so well if you get that effective temperature right, that reference temperature right. It is amazing. When I first started, we learned it, but a lot of people didn't realize, I think, how powerful that equation is in similitude.
Yeah, I'll dig that reference and send it to you.
Okay, all right.
I'll have to ask my colleague again, though.
Yes.